Hi, I'm Andrew Rosen, and this is my presentation for my capstone project for the Engineering Honors Program. Um, the project is titled Parallel Processing for Satellite Images, and I did it through GeoStar Remote Sensing Analysis Platform. I actually joined GeoStar as part of an MVP project during my freshman year, and the problem that we're trying to deal with is that satellite images are pretty challenging to work with. In general, when new imaging satellites go up in space, the file format of the images tends to change. And so there hasn't really been software to kind of standardize these images and be able to work with them together. And a lot of the software ends up being kind of outdated. So our goal is to make a standardized solution for all types of satellite images, um, and make a pretty comprehensive library to enable image processing over those. So kind of over the past couple of years, I've been working on pretty standard image processing features um, on pretty regular images as well, like the one you see on this slide. Um, it's kind of important, if we're going to talk about it, that you guys know what the structure of images are in computers. Essentially, we have a matrix of pixels. And so pixels are really just a number value from generally 0 to 255, although there's all kinds. Um, and kind of the most rudimentary image is a grayscale image. And so each pixel takes a value from 0 to 255, whereas 0 is black and 255 is white. And it's sort of a spectrum between there. And so, for example, in this case, 125 is that gray color. Um, and well, this is like a pretty rudimentary one. There's a lot more than just this. For example, like an RGB image, it actually has three channels, so red, green, and blue, unlike just the grayscale channel or the one channel in the grayscale image. And these channels sort of stack on top of each other, and so they're still the same size. They can have different values for red, green, and blue in each pixel, and when they are put together, you get something that looks like an image you're probably more used to seeing. And there's no reason to stop at three. We actually can have as many channels as we want. And for example, in like a PNG image, they'll add an alpha channel for transparency. And that's the type of image that has like a transparent background or something like that. Um, Now, satellite images in particular can have lots of channels. Um, I know they can get up into double digits and up almost into like the 20s. So a lot bigger than kind of the standard images that we work with. And this is actually a problem. So satellite images are really large. They have lots of channels and also can be very big dimension-wise. In the scale of like 60 to 70,000 is normal, and that's too big for RAM memory in a computer. And so on top of that, a lot of these remote sensing analysis jobs are run on high-powered computing clusters with parallel file systems, so HPC clusters. Um, and so in order to leverage that, you need to be able to run your code on multiple computer nodes and have them still work together. But at the moment, GeoStar can only be run serially. So kind of what my goal is for this project was to add concurrent capabilities across GeoStar, and kind of give us the ability to leverage high-powered computing clusters for these really large images. And so sort of from the beginning, the way that we standardize what these images are is this hierarchical data format 5, or HDF5, and it sort of treats a file like it's its own file system. So you have a file, and then below that groups, and below that data sets. And this is actually a pretty nice way to generalize images, and in particular satellite images. So if you take a look at it, there's an HDF5 file, group, and data sets. And we just sort of organize it in a tree where the file has an image within it, and an image can have these GeoStar rasters, which is the same thing as a channel. And the raster data set is just a matrix of numbers. So we treat it very similarly to how you would imagine an image would be. Ultimately, what I decided on for my design was to use this HDF5C interface with OpenMPI, which is an open source software for multi-process coding. So essentially, it gives us the ability to have our code running in multiple processes on a computer at the same time. And this is how we can then make GeoStar parallel. The other thing was that in order to validate that my code was actually working, I had to make a compute cluster on Google Cloud, which would give us a parallel file system. And so we could scale up to see how adding more CPUs and more processes actually speeds up our code. And so the implementation that I actually took from the code perspective was a parallel file, a parallel image, and a parallel raster class, which pretty much work pretty similarly to the original ones. You can create open files, create open images, and so the way that you would go about doing this is you create the file, open an image within the file, or create an image within the file, and then create a raster within that. And so this is kind of the most important, um, because a raster you can read a slice and write a slice in parallel, and that's sort of the primary focus of what I did, because pretty much any feature that we've done on top of that just depends on reading and writing. And so all the features that we built for the original raster class can now be built on top of this parallel raster class pretty easily. Um, the other thing was that I had to make a pseudo-HPC cluster. And so I didn't have access to one during development, so I kind of had to build and configure my own system. Um, the two requirements I needed were compute nodes to scale up the number of processes. So this would be running the actual GeoStar code on it, and hopefully a benchmark test to see how fast it gets as I add more processes to make it more and more parallel or more and more concurrent. The other thing I needed was a parallel file system. And I'll get more into why that's important up next. But I had limitations just because I had to work within one of the tiers of Google Cloud. So I had $300 in credit and a maximum of 24 virtual CPUs. What this ended up looking like and why this parallel file system was important was because RAM is small and fast, but disk I/O is very slow. And so because these satellite images are so big, they don't fit in RAM, and it leads to a lot of disk I/O. And that's ultimately the biggest bottleneck. And so even with parallel processing, if computations are waiting for processes or are waiting for disk I/O, it doesn't matter if we have multiple processes because they're all waiting for kind of the biggest bottleneck. So what I ended up using was Lustre file system. It's an open source software that lets you manage a parallel file system pretty easily. And the idea is that when the file system is distributed over lots of machines, disk I/O can actually happen in parallel because there's multiple disks. And ultimately the goal was that for these satellite images, if I add a parallel file system, I should see speedups on a cluster. And so what I actually built, if you look at the Lustre MDS and Lustre OSS nodes on the right, the idea here was essentially the file system is distributed over 4 OSS nodes, and it's managed by that MDS node. And so I could then mount that on other computers. So I had a compute node with a scratch directory. And so that scratch directory interfaces just like any other directory. So I could read and write to that from the computer. But what it was really doing was going over the network in this virtual private cloud I have, and being distributed over multiple machines. The compute node would ultimately be where I run code. So I actually wrote kind of this benchmark test where I would collectively create a file, and each process has a unique ID when I run it. And so based on that ID, I could split up the image. So for example, for an image or for one process, I would just have it handle the entire image. But for 2 processes, I would make one handle the top half and one handle the bottom. For 3, I could do 1, 2, 3, etc. And so the idea was I could then scale this up and see how the performance improves with this benchmark test. I ended up picking a really large image, so 73,728 by 73,728, because that number is equal to 2 to the 13 times 3 squared, which means it can be cleanly divided by 1, process 2, 3, 4, 6, 8, 9, or 12. And so I would then have kind of 8 data points that I could look at to see how much this actually improved. And so I automated a test to make it run 50 times for each of these number of processes, and I found that 12 processes was about 20% of the time as one process took. But when I look at the actual graph, it starts to kind of flatten out at around 6 processes, which leads me to believe that it's possible the parallel file system was stopping it earlier than it should have, or slowing this earlier than it should have. And so my end goal, I think if I were to do future work on this, would be to evaluate it on an actual high-powered computer with an actual parallel file system. That's all I have. I want to thank Leland Pierce for being my faculty advisor, and thank you guys for listening. Feel free to ask any questions, and thank you.